What did we end up with yesterday? What reaction?
Lead to iodide.
Okay, lead to iodide. That one's tricky too, because we expected the lead 2 chloride to be less soluble, the lead 2 iodide to be more soluble, because the lead 2 chloride had stronger ionic bonds. But the bonding there was tricky, and our prediction was wrong, right? That's what happened. And so there you go again, silver, lead, mercury, some of the other heavy metals. All right, we're looking at acid-base reactions today. There are 3 different types of acid-base reactions. Actually, there's only one type. One type, we could describe all acid-base reactions as Lewis. But describing them as Lewis is more difficult than subcategorizing them. If we subcategorize them, well, Arrhenius isn't a very useful subcategory because Arrhenius acids are H plus AQ or hydronium AQ. Arrhenius bases are hydroxide AQ. And so there's only one Arrhenius acid-base reaction, that is H plus OH minus yields water. Bronsted-Lowry is a very useful subdivision. The most comprehensive definition is Lewis. You know, Lewis, you'll cover every single acid and base out there. Bronsted-Lowry, you're going to miss some. You're going to miss some, but you know, Bronsted-Lowry is so easy to use. If we can use it, we'll use it. And then if we have to, we'll fall back on Lewis. But Lewis is just a bit more complicated, and we would try to avoid it if possible. And so let's take a look at the Bronsted-Lowry acid-base method. Bronsted acid is a proton donor. A Bronsted base is a proton acceptor. So an acid-base reaction here is just a transfer of 1 proton from the acid to the base. Then we look for the driving force. Driving force is always going from stronger. Stronger acids are more reactive, less stable, to weaker. Weaker acids are more stable, less reactive. So we always want to go from stronger, more reactive, less stable, to weaker, less reactive, more stable, in both acids and bases. And then we determine if further reaction occurs. For example, we might have a diprotic or triprotic acid. And so we might see something like that. And so the method that we're going to use is inventory, which we'll talk about. Then we're going to determine the strongest acid and the strongest base present in the inventory. And then we're just going to transfer a single proton from the strongest acid to the strongest base. Those 2 species will be the most reactive species in the mixture. Then we'll determine if a driving force is present. And then we'll repeat it if further reaction occurs. So let's go ahead and use the method. We're going to apply this method to this. So for a second. Some reactions, they fit more than one category. And so if we look at H3PO4 and sodium hydroxide, H3PO4, do you recognize that acid? What's that called? Phosphoric or phosphoric acid and sodium hydroxide. There are 2 ways to do this. We could do this via metathesis or, Bronsted. We handle these 2 differently depending on which approach we take. If we do it to metathesis, we do complete reaction. Versus if we do it Bronsted, we do it 1 step at a time. So if I were to do this by metathesis, I would completely neutralize all the hydrogen. I have 3 acidic hydrogens here. And so I take H3PO4 plus sodium hydroxide. I'll balance this later. is going to form what? This is just double replacement reaction. In a double replacement reaction, what would be formed? Na3, PO4 plus H2O. Since we're completely neutralizing, I'll need 3 sodium hydroxides and 3 waters to do that. Then we have driving force here. This is the stronger acid. What's the weaker acid? The water. This is the weaker acid. This is our driving force. So we're going from stronger acid to weaker acid. That's all we need. We just need one driving force in metathesis. All these are AQ except for water, which is liquid. For Bronsted, we handle this differently. For Bronsted, the first step is we're going to inventory. What do I mean by inventory? What I mean by inventory is this. We see what major species are present. So if I have H3PO4 and sodium hydroxide, then H3PO4, does that split apart as a strong electrolyte? Or is that a weak electrolyte? It's a weak. Phosphoric acid is weak acid, and therefore it's a weak electrolyte. And therefore we just leave it alone because the major species in solution are going to be molecules of phosphoric acid. Okay, a little bit of it will break apart into ions. Sodium hydroxide, is that a strong electrolyte? It is. Soluble salt. Sodium salts are all soluble. And so we're going to have sodium ions and hydroxide ions from sodium hydroxide. Hydroxide is a strong base. This would be our Arrhenius base. You know, we got hydroxide in solution. When we think about strong bases, the strong bases are the soluble hydroxides. So for example, group 1, calcium, strontium, barium are all strong bases. What about something like magnesium hydroxide? It's insoluble. So if it's insoluble, we would consider it a weak base or very basic. And so this is why, you know, you wouldn't want to eat sodium hydroxide. Sodium hydroxide is drain cleaner, it'd kill you. But some people eat or consume magnesium hydroxide, which is like milk of magnesia, which won't kill you unless you eat too much of it. But having too much of anything, including water, will kill you. So everything's toxic to some degree. So anyway, is there anything else present, or do I have it? These are the major species I expect to find in this mixture, except I'm missing one. What? Water. I'm missing water. So, there. Now I have the major species. So that's my complete inventory of this mixture. Inventory of the mixture. And then I figure out the strongest acid base present, so I have to label all these. Phosphoric acid is an acid, so I'll just label it with an A. Sodium ions. Is that an acid or a base? Well, it's a spectator. So what we call that is neither, or neutral. Because sodium ions do not donate a proton. Do sodium ions have an H to donate? No. Do sodium ions accept a proton? That is it possible for sodium to pick up an H plus to form NaH2 plus? No. This doesn't make any sense also. We call it neutral. Hydroxide. Hydroxide's a base, right? Hydroxide's a strong base. But hydroxide will trick you, because if you look at the acid chart, you'll notice something about the acid chart. And that is the left column's the acids. You see? Hydroxide's in the left column. Is that a mistake? No, it's not a mistake. Hydroxide's in the right column in the base. And so hydroxide is what we call amphoteric. Hydroxide can lose a proton. If hydroxide loses a proton, what does it form? If hydroxide loses a proton, its conjugate base is oxide, a more powerful base. So hydroxide can act as an acid to form oxide, or hydroxide can act as a base to form water. And so hydroxide is amphoteric. We don't care about the strengths. Hydroxide is a very, very, very weak acid and a very, very powerful base, but it doesn't matter. It can go either way. And we don't know which way it's going to go until we react it with something else. Water, on the other hand, is equally good either way. And so water is equally good at picking up a proton or losing a proton. And so it's both an acid and a base. But we don't have to make any judgments about which one's stronger, because all we have to do is look at the chart. And so when we consult the chart, we look for the strongest acid. In fact, do you even need the chart to figure out which is the strongest acid here? We don't need the chart because, you know, phosphoric acid versus water, for sure phosphoric acid. Phosphoric acid versus hydroxide, for sure phosphoric acid. And so we don't really need it. Phosphoric acid is going to be the strongest. Do you need the chart to figure out what the strongest base is? We don't really need it there either, but you can always use it. You know, if you don't want to think about it, you can just use the chart. And you don't have to think. Let's go ahead and use the chart. We have two bases, hydroxide versus water. If I didn't want to think about it, I just want to use the chart. Here's hydroxide. The strongest bases are at the bottom right in this chart. And where's water? Water's way up here. Water's much weaker. The strongest base is going to be hydroxide. And then we react the strongest acid present, H3PO4, with the strongest base present, hydroxide. And we're going to get, what are we going to get? We'll figure it out. H2PO4, 2 minus. If it loses an H plus, well, there are different ways we can do it. Phosphate, you know, what is the charge on phosphate? 3 minus. And H plus, yeah, it'll be minus. So we have two H pluses and a phosphate combined to make an H2PO4, which is just going to be a minus. Didn't show it. It's not going to split apart because it's a weak acid. Only strong acids will split apart like this. H2PO4 minus plus H2O. Excuse me. We already labeled this. This is our acid, this is our base. But we have to imagine this as being competition. There's a forward reaction here competing with a reverse reaction. And so if we were to reverse this reaction, that is, if we were to go backwards, what would the acid, what would the base be? Well, both of these are amphoteric. Both of these can act either as an acid or base. But the way they react is defined by what they're reacting with. And so what we look at is H2PO4 is both an acid and base, but in this reaction, it's going to act as the this is going to be the base. The base is correct. This is the base. How? You know? Because if we went backwards, H2PO4 gains a H to go to H3. So this is going to be the proton acceptor, which is the base. When water loses a proton to form hydroxide. This is going to be the acid. And so we determine what the identity is based on the reaction it undergoes or what it's reacting with. All right, now to figure out the driving force, we compare the two acids. Phosphoric acid versus water. Which one's better at neutralizing sodium hydroxide? Or, you know, which one do you think is better at neutralizing base? Is phosphoric acid or water? Phosphoric acid. And so here we don't really need the chart. We could just use what we know. Hydroxide versus H2PO4 minus. Hydroxide. And so what we have here is driving force. We're going from stronger, more reactive, less stable, to weaker, less reactive, more stable. And that's our driving force. Stronger to weaker. So this is what we just did. Again, on tests, I'm not going to give you the formula on tests, I'm just going to give you the name and expect you to write the correct formula. And note the difference with metathesis, or the double replacement approach. Now let's take a look at this. Solutions of sodium monohydrogen phosphate and potassium hydrogen sulfate are mixed. Let me mark this up here. All right, somebody give me the formula for sodium monohydrogen phosphate. Na2 HPO4, that's correct. Na2 HPO4. AQ, potassium hydrogen sulfate. K2 or K? KHSO4, that's correct. A lot of people think of this as double replacement because it's an AB plus CD. You know, when you look at a compound like this consists of two sodium ions and a hydrogen ion and a phosphate ion. Is that right? No, we don't split this apart because it's not a strong electrolyte. We only split apart strong electrolyte. So we leave this intact. It's an HPO4 2- ion. And so some people think of this as metathesis. What we'd form is potassium hydrogen phosphate or monohydrogen phosphate and sodium hydrogen sulfate. Be no reaction there. And so even though this fits the AB plus CD pattern, we get NR. But that doesn't mean there's no reaction, because there are other types of reactions that can occur. In addition to double replacement, what are they? There's acid-base and redox. And so what we're going to do is we're going to look at the acid-base. So let's inventory this solution first. And I'm going to do it for you because we're short on time. Even though there are two sodiums, I only inventory one sodium because, I just have sodium present. We got to balance it at the end anyway. And so I just want to see what species are going to react and balance it later. Now, how do I treat HPO4? Do I leave it together or do I separate it? We leave it together, so it's going to be HPO4 2-. What about this? K plus and HSO4-. Again, HSO4- is a weak acid. Weak acids, we do not dissociate. And so we leave it together. Okay, is this the complete inventory or are we missing something? Yeah, we're missing water. Why do we care about water? And the reason we care about water is water can act either as an acid or a base. And so we need to factor it in. Sodium ions, neither are neutral. HPO4 2-. HPO4 2- is weak acid and a weak base. It's both. The chart, unfortunately, that I gave you on the PowerPoint it had some mistakes in the last. Well, not mistakes, it just omitted something. This chart should have H3PO4, should be the strongest, H2PO4, and HPO4. But I didn't edit it this last time, but the last person who edited it knocked those out. And so if we look at this chart here, you can see it. There's H3PO4 here, and then H2PO4 in the middle, and HPO4 minus down here. Somehow those got left off that. They got left off this not because those are important, those are very important. And so I have to look at my chart. On tests, I'm going to give you this chart so you don't have to memorize it. You know, one student asked me, should I memorize the chart? You know, they really wanted an A, so they were willing to memorize that chart, but what do you think? No. You don't have to memorize the chart, but does that mean I don't have to memorize it? I can just completely ignore it now. Is that a good idea? No, that's not a good idea either. What you want to do with charts is this. Have you ever heard the term data reduction? Data reduction? You've heard it? In what context?
Three data to make sure that that's enough. Any more would be too much or any less.
Okay. Maybe 3 was the statistically valid number of experiments, something like that, to minimize the error. Data reduction is used in different contexts. Data reduction is, you know, the scientific method. Scientific method, what do scientists do? They collect observations. How many observations do they collect? Tons of observations. So you got data charts with 50 pages. And so what do? Do you sit there and memorize each observation? Each piece? No, you don't. What do you think they do next? They make it into a table. So they got 50 pages worth of tables. Then what do you think they do? They look for patterns. And so I don't say memorize the chart. I say look for patterns. Do you see any patterns in this? We talked about patterns last semester. I don't know. Did you guys talk about these patterns? HI, HBr, HCl. There's a pattern for you right there. Do you guys remember the reason for this pattern? Why is HI a stronger acid than HCl? Higher ionization? No, not exactly. And why is HF so far out of the pattern? Not because of its electron negative. It's because of this. There's certain factors in that. And so you don't really want to memorize each entry, but you want to memorize the patterns. There are multiple sets of patterns in this chart, and so it's very complicated. But you look for those. You look for those, you know, structurally or compositionally or whatever. And we seek those out and then we try to understand. Because this chart, do you think this chart is comprehensive? Absolutely not. There are lots of acids and bases left out of this chart, right? And so what happens when you get an acid not on the chart? Well, some people say, oh, hey, that's not fair. That wasn't on the chart, right? Well, you know, that's an acceptable answer, but that's not an answer that the top student would give. You know, the top student would say, well, they could figure it out based on the pattern, right? And so even though the acid wasn't on the chart, they still figured it out because they recognized how it fit into one of these patterns. And so, anyway, we're going to take this at different levels. And so, if you don't want to deal with patterns, you don't want to deal with any of that, then you should at least understand this method to the basic level. I say, and this I said last semester in Chem 1A, that, you know, this might be a little difficult, but once you have this, an elementary student with no understanding of chemistry can do this, can figure out the answer. You don't have to understand any chemistry. You don't have to understand this chart. All you have to do is be able to use the chart. You know, which one's higher, which one's lower. That's it. Right? What tends to happen is that people get into some kind of mind block where they think this is so difficult they can't do it because then they start overthinking. But you don't want to start overthinking this because it's actually quite easy to do. Okay, then once you master these steps, then what you would do is start trying to understand this more deeply and see, you know, what are the particular patterns for acid and base strength. And so let's go back to this. figure this out. So HPO4 2 minus occurs on both sides, and so we call them acid and base. It's amphoteric. Potassium ions, neutral. HSO4 minus is an acid and a base, either proton acceptor or donor. Water, acid and base, amphoteric. We don't care about the strength differences. For example, HSO4 is a much stronger acid than it is a base, but we don't know which way it's going to react. Even though it's a much stronger acid, it still might react as the base, depending on what we react it with. All right, so then we pick the strongest. So the strongest, we just look at the chart. You know, we have 3 acids here. What's the strongest acid on the chart? On that chart, it's HClO4. Do you guys know when you get a chart, you should look at the extremes? Do you guys remember what the weakest acid was on the chart? On the chart that you saw yesterday? You know, you might not want to memorize all the entries, but you should always memorize the extremes. What's the strongest and what's the weakest? Because at least if you have the extremes memorized, that's a very simple pattern, and then you could try to think through, you know, something in between. So nobody recalls that probably, but no. The weakest acid on the chart was, there it is, this, methane. Is methane good at neutralizing base? No, methane's not good at neutralizing base. In fact, methane's not going to react as an acid with any base you probably know. What kind of base would you need to react methane as an acid? And why would somebody be interested in reacting methane as an acid? Well, we look at the strongest base on the chart. What is the strongest base on the chart? Strongest base on this chart is methide. Is methide enough to neutralize methane? No. Because methide and methane will just produce methide and methane. So we get no reaction, right? We need a base stronger than methide. Are there bases stronger than methide? Yes, there are, you know, super bases. Are there acids stronger than perchloric acid? Yeah, there are. There are acids stronger than perchloric acid. So we got the super acids, super bases. Those aren't that common, you know. But there's a professor at USC, George Olah, who won the Nobel Prize recently for his work on superacids and superbases. The reason is he's trying to make things, you know. If you could take methane and make it react, maybe you can make synthetic gasoline. Or maybe you can take methane and make methanol. Or maybe you can make many different things. And so this is why people are looking for these exceptionally reactive species out here to make different things. But we don't have to worry about that. We just have to use this chart. And so let's figure out what the strongest acid is. And so here's H3PO4. And if you know some patterns, HPO4 2 minus should be weaker, somewhere down here. That chart has it. And then we compare it with HSO4 minus. HSO4 minus is way up here. So HPO4 2 minus has got to be a lot weaker acid than H3PO4. And so, and then water's going down. And so the strongest acid is going to be HSO4 minus. What's the strongest base going to be? I wouldn't throw this at you initially. You know, I'd give you a chart like that with all the entries in. But HPO4 2 minus is going to be the strongest base. And so that's part of this data reduction mentality, is looking for these patterns, you know, so you don't have to memorize individual, but you memorize patterns in those, which are much more useful. And so let's come up with the reaction here. And the acid is going to lose the proton, so HSO4 minus. The base is going to gain the proton, HPO4 2 minus. So we have an acid-base reaction. What are the products?
Water.
There's no water in this acid-base reaction. You usually, you memorize that pattern. Acid plus base yields water plus salt, right? That pattern doesn't work for these. We don't make sulfuric acid. We could if this acting as a base, but it's not acting as the base. This is acting as the acid, this is the base that defines how the reaction goes. What are we gonna make? Well, the acid gains or loses. The acid loses, so we're going to be left with SO4. We just got to figure out the charge. It loses an H plus, so it loses one positive charge, which makes the charge less. So we form sulfate. The base gains a proton, so it's going to have not one but two hydrogens. So it's going to be H2 PO with a minus charge. All right, now we imagine this reaction going backwards. Going backwards, what's the acid, what's the base? Yeah. And then we use the chart to compare the two acids. Which one's a better acid, HSO4 minus or H2PO4 minus? Looking at that chart over there, HSO4 minus is stronger, H2PO4 minus is weaker. The bases have to follow, so looking at the chart there, HPO4 2 minus is stronger, sulfate is weaker. And so again, we have a driving force. So there was no metathesis reaction here, but there was a acid-base reaction, or there is an acid-base reaction that occurs between these species. All right, solid sodium amide is mixed with water. In this case, I emphasize solid because all sodium salts are soluble, right? But why do I call it solid sodium amide rather than aqueous? Because there's water present, so it should dissolve, right? The reason is because of amide. Do you guys know what amide is? NH2 minus. And why is amide important? Why amide's important is what is the strongest base on that chart? NH2 minus. What is NH2 minus called? Amide. And so amide's the strongest base on that chart. It's weaker than methite. And sodium amide would be, this is Na plus, this would be NH2 minus, so this would be a 1-to-1 ratio. That would be sodium amide. Why do I say solid? Because you guys should memorize the strong bases. The strong bases are stable in water? No. The strong bases hydrolyze water 100% to form hydroxide. And so this particular reaction in water, well, let's go ahead and figure out the inventory for this. We know that this is soluble. If this is soluble, then we inventory this. We're going to get sodium ions, AQ, amide ions, AQ, and we have water, liquid. But automatically you should see amide. Now amide's not going to be stable in water, is it? And so, well, we could do this by acid-base as well. Sodium ions are neutral. Amide is a base. Amide could also be amphoteric. You know, bases are proton acceptors. If this accepts a proton, we should form NH3, but it could also lose a proton. If it loses a proton, it forms an even more powerful base than amide. If amide loses a proton, we'd be left with NH with a 2- charge. NH with a 2- charge should be a super base. You know, it should be something very, very powerful. And so technically this is amphoteric, but we aren't dealing with super acids and super bases, right? And so what we're gonna do is we're just gonna call it a base. What about water? Water is both. And so the strongest acid present, well, there's only one acid present, water. The strongest base present, amide. And so the reaction is going to be between amide and water. So amide and water forms what? It's going to form NH3, the charge, no charge, and hydroxide. So this is what we mean by strong bases. Strong bases, they don't ionize. Strong bases hydrolyze 100%. They're strong electrolytes. Because a strong base in this case is amide. Well, there must be a good driving force for this. So let's go ahead and figure it out. Amide's the base, water's the acid. If we go backwards, what's the acid? What's the base? Wait a minute, both of these are bases, aren't they? This is base and a base. Oh, you're right, hydroxide can act as an acid as well, so that means ammonia is the base and hydroxide is the acid? Is that correct? Ammonia is the base and hydroxide is the acid? No. No, we don't worry about that. We don't worry about our ideas. We just look at what happens. Acids are proton donors, so who loses an H? Ammonia or hydroxide? Ammonia loses an H. So we went from NH3 to NH2, so therefore ammonia must be the acid and hydroxide the base. So, and so ammonia is the acid. Is ammonia an acid? Yes, ammonia is an acid. Do you see it? Ammonia occurs both on the left column and the right column. Ammonia is amphoteric. But we're biased to think ammonia is a weak base, right? But it depends on what you react with. And so, anyway, going to this, which one's a stronger base, amide or hydroxide? Amide's a stronger base, hydroxide's a weaker base. Water versus ammonia, which one's a stronger acid? Water is a stronger acid. Ammonia is a really bad acid, pretty decent base. And so again, we have a driving force here.
Professor, is it safe to assume that the strong acid and base will always be on the reactant side?
No.
Why not?
Sometimes the strong will be on the product side. What do we do there? There are two things we do when it's on the product side. For example, H2O liquid plus H2O liquid. I'm going to call this the acid, I'm going to call this the base. The acid is the proton donor. So we form hydroxide and hydronium. We say, this is the base, this is the acid here. Here, this strong is on the right side. So we do two things in this case. One, we say that there's no driving force, therefore no reaction. No reaction. But you might have seen this reaction before. Have you seen this reaction? Utima, have you seen this reaction? Yes, we've seen this reaction before. We saw this reaction in Chem 1A when we were doing pH. Right? The pH of water is pH 7. pH stands for power of hydronium, power of hydrogen ion concentration. So even though there's no driving force for this, a tiny bit of reaction occurs. That tiny bit of reaction that occurs gives water its pH. If we didn't have any reaction here, then the pH of water would not be 7. And so we do things at different levels. We do things at different levels. The first level we're doing is we're treating this as black and white. We treat things black and white sometimes in this way. insoluble versus soluble. If it's insoluble, it doesn't dissolve. If it's soluble, it dissolves, right? But you saw, even insoluble solids, a tiny bit dissolves, like silver iodide, lead-2 iodide, lead-2 chloride. Even though we say there's no reaction here, a tiny bit of reaction occurs. This tiny bit of reaction gives water its pH. This tiny bit of reaction that occurs, NH3 plus water. NH3 plus water gives us NH4 plus hydroxide. We're going from weaker to stronger. So we'd say no reaction, but we know a tiny bit of reaction occurs. The tiny bit of reaction that occurs in these types of reactions is what we call an equilibrium, because both forward and reverse reaction occurs. And therefore, our main goal this semester is to be able to do stoichiometry calculations based on this. In Chem 1A, the stoichiometry would be so simple. 0, 0. 0 grams, 0 moles are produced, 0 grams, 0 moles are produced. But in Chem 1B, we want to figure out what that tiny amount is. In Chem 1B, we figure out there are 4 out of a billion water molecules will do this. In Chem 1B, we're going to figure out there's going to be 0.01 molar. Just going to give it a pH. And so right now we're doing Chem 1A style. But we need to get this Chem 1A style so that we know that our Chem 1B calculations make sense. You know, we got to have a mental idea of what's going to happen, you know, to help us do the calculations. This method, you know, what happens is this. As soon as I do this, then this, you know, let's say a certain percentage will get this in the class. But if I went ahead and did this, then all of a sudden the percentage that would get the right answer has dropped dramatically. In fact, the percentage of people with a blank page will increase dramatically because now people have no idea how to do this problem. You know, just by throwing in a couple of spectator species, it screws people up. Or, you know, I'll throw in some more, plus, etc. It doesn't matter how many I put in there. You know, the approach is the same. The approach is you would inventory, you know, and it doesn't matter if you have 10 items in the inventory or 1,000 items in the inventory. Even if you have 1,000 items in the inventory, you just pick the 2 strongest, right? And so even though I threw in calcium nitrate in here, the reaction's exactly the same. Because calcium nitrate turns out to be not the strongest acid nor the strongest base. And so those are just spectators. Watch out for that because sometimes I'll do that on tests. All right, now once you've mastered this, the thing is don't overthink this, just be able to do the method. You know, being able to do the method, I could throw 5 reagents in here and you should still be able to do the method, right? Okay, now doing the method is like the pass or whatever, you know, that's good. It's always good. But, you know, if you want to understand more deeply things, then let's look at the reactivity. Identification. And so we started this in Chem 1A, you know, looking at the end of chapter 16. You guys remember that? Why is HI a stronger acid than HCl? Somebody tell me. You remember it, Tima? What about the structure of HI makes it a stronger acid than HCl? Okay, Anthony?
The ability for it to like above the icons of the sign.
Yeah, that ability is related to bond strength. So that was a bond strength issue, right? That was the pattern. But there are multiple patterns in this. Because not only was bond strength one of the patterns, but what was one of the other patterns we saw in acid strength? Well, that works for HI to HCl, but you know, when we look at some of the other acids, it doesn't work because the bonds is the same. It's an HO bond. So they all have the same bond strength. And so then we looked at something called bond polarity, right? And then for HF, HF was outside the pattern, and HF had to do with product stability, the ion pair formation. If you didn't cover chapter 16 in Chem 1A, and then this morning a lot of the people said they didn't really cover chapter 16, the end part. End part of structure, of chapter 16 deals with structure and acid strength. That's okay because we're going to cover it again. Probably not, we're not going to spend as much time though, so it's just going to be briefly reviewed. But these are the patterns we can find. When we look at that chart and look at the acid strengths, these are the patterns I see: bond strength, bond polarity, product stability, and there's others here too. But these ones you want to look for. And so when we look at this, one, we could look for the patterns, or two, we can analyze these more, deeply. And so how do we describe structures from a theoretical perspective? Well, when we describe structures of acids, we typically use Lewis structures. Lewis structures are going to be based on quantum mechanics. And so if we're doing pencil and paper, we just draw out the Lewis structures and then look at these items here, try to figure it out. If we want to go into this in great depth, then what we do is quantum mechanical calculations. When we do these quantum mechanical calculations, we generate these electrostatic potential maps. And so here's a comparison of acetic acid versus sulfuric acid. Which one's a stronger acid? Well, we see these red and blue regions. And if we're looking at acid strength, we're going to focus on the red regions or the blue regions? The blue regions, because the red regions, this is a little bit backwards, because red is negative charge density or positive charge density. Red in electrostatic potential maps is negative charge density, which is confusing because the red terminal on batteries is the positive terminal, not the negative terminal. And so this is exactly opposite of what most people think. Most people think red is positive, blue is negative. Unfortunately, whoever assigned the colors decided that blue is positive, red is negative. And so if you're a base like hydroxide, which of these two acids are you going to be more attracted to? Hydroxide would like to attack acetic acid, or would it like to attack sulfuric acid first? Hydroxide's negative. Hydroxide's negative, it's looking for positive. Which one of these is more positive? Sulfuric. And so this is why we say the more reactive, or the more stronger species will be the species that react. Because if there's a competition here, for sure, hydroxide will attack sulfuric and ignore acetic, right? All right, so electrostatic potential maps can help us, but generating these electrostatic potential maps and also quantum mechanics is much more, because it'll tell us the bond energies, the geometries, everything else that we need to know. But if we don't have quantum mechanics program like Spartan, then we have to do this with pencil and paper. And so most of the time we're going to be working with pencil and paper. And so quantitative quantum mechanic calculations, most people don't have access to. And so we're going to do qualitative. And so how can we figure out, because chemistry is all electrical attractions, acids are positive, bases are negative. And so when we look at those electrical attractions, Then we're going to break it down into simple ways of counting electrons or figuring out how the electron density is distributed without looking at the orbitals just yet. And so when we count electrons, there are three ways to count electrons. We can count the octet. The octet is the total number of electrons surrounding the atom. We can count electrons using formal charge. Formal charge assumes what? It assumes the bonds are 100% not ionic, covalent. Formal charge assumes the bonds are 100% covalent, so if you have bonding electrons, they're split 50-50. Oxidation state assumes the bonds are 100% ionic. And then we have some bond polarity. Bond polarity is somewhere between the two extremes.
So which one assumes that the bonds are covalent?
Formal charge assumes all the bonds are 100% covalent. Oxidation state takes the opposite assumption and assumes the bonds are 100% ionic. All right. So we're going to use that. We can use that in looking at these acids here. We can use that in looking at these, which are more complex. Lewis acid and bases, this is the most comprehensive definition, and all acid-base reactions react in this way, including Bronsted. But when we think in this way, it just makes things more difficult. For example, ammonia, we recognize this as a base, mostly. But BF3, do you recognize that? No. BF3 turns out to be a powerful Lewis acid. How could I recognize it as being a Lewis acid? Well, one, I count the electrons. What do you notice about BF3? What's unusual about it? It only forms 3 bonds, and there's no lone pairs. In other words, this has less than an octet. It needs 2 more electrons. The fluorine's organic chemists are notorious for this, and I got this off an organic site. There should be lone pairs around fluorine. A double bond doesn't form. You know, we can make an octet here by taking a lone pair and making a double bond. But we don't do that because that would increase the formal charge on fluorine to +1. Fluorine hates a positive formal charge, and boron would get a -1 formal charge. And so we don't double bond fluorine. And so this makes this electron poor. Now in Lewis acid-base reactions, the base is electron pair donor, the acid is electron pair acceptor. So we have ammonia here with an electron pair, boron, which is lacking electron pair, and then we can have a Lewis acid-base reaction. What forms in a Lewis acid-base reaction is something called a coordinate covalent bond. A coordinate covalent bond, both bonding electrons come from one atom. In a typical covalent bond, one atom supplies one electron, like hydrogen. Another hydrogen would supply the other electron, and they would share those 2 electrons. Right? In a coordinate covalent bond, boron supplies no electrons. In this case, nitrogen supplies both electrons, and we have a covalent bond formed here between nitrogen and boron. This covalent bond that results here, you can't tell the difference between a normal covalent bond and a coordinate covalent bond once it's formed. Coordinates just assigned to the formation process. Now, this results in a formal charge. We didn't have formal charges over there, but now we have formal charges, and formal charges are not good because it's charge separation. Charge separation creates these voltages, and those are unstable. And so we have to weigh the difference. What's more stable, having an octet around boron or having an unstable formal charge arrangement? It turns out having an octet around boron is more favorable. And so this actually happens, this reaction, and we end up with these formal charges like so. All right. Identifying Lewis acids and bases is a bit more difficult than identifying Bronsted acids and bases. And so normally when we try to identify Lewis acids and bases, like BF3 being a powerful Lewis acid, we'll just look at its structure. And then what we do is we look for electron-rich areas, high negative charge density. These electron-rich areas, we want them to have a lone pair so that they can act as an electron pair a donor. And so we look for red regions here. The red regions would be the base regions. And we need to make sure that they're lone pairs that can be donated. And then we look for electron poor areas, areas with high positive charge density that are capable of accepting an electron pair. And then we'd like to come up with a table. We'd like to come up with a table that ranks the Lewis acids and Lewis bases, but you're going to be hard pressed to find a table. In fact, you aren't going to find any table unless you're looking at a subset of Lewis acids and Lewis bases. There's not going to be a more comprehensive table of acid-base strengths. The reason there's not going to be a more comprehensive table is because of the covalent bonds that form. When you form a covalent bond, you're looking for good orbital overlap in valence bond theory, or you're looking for similar orbitals to do an LCAO. Do you guys remember the acronym LCAO? Linear combination of atomic orbitals to form molecular orbitals. Well, both of those in MO theory and valence bond theory are similar. You want similar sized orbitals. So for example, if you have a gigantic orbital overlapping with a tiny orbital, are you going to get good orbital overlap? No. What you want is you want a gigantic orbital overlapping with another gigantic orbital. In other words, two big orbitals overlapping. Or you want two small orbitals overlapping. But you don't want disparity in the orbitals because that makes poor orbital overlap or makes poor LCAOs for MO theory. This is simplified using HSAB when we're thinking about orbitals, what makes a good matching pair of orbitals. HSAB stands for hard, soft, acids, bases. So a hard acid or hard base would be small orbitals. A soft acid or soft base would be big orbitals. So big orbitals are more polarizable, softer, right? And so HSAB can be used in understanding lead iodide versus lead chloride. Lead, big and soft. So big and soft like soft. What's softer, an iodide or a chloride? Iodide. Iodide's bigger orbitals, softer. So soft likes soft. Lead likes iodide. Chloride's much harder. And so lead and chloride aren't as good of a match. Do you see how the covalent interaction interplays with our idea of ionic? And so the first thing we're going to look at is something that you might not recognize as the acid or base, and that is CO2. I already told you what CO2 is. CO2 is an acid, but CO2 can also be a base. And so let's take a look at CO2. CO2 is a Lewis acid and a Lewis base. And so let's analyze its structure. When we analyze the structure of CO2, we look for electron-rich areas and electron-poor areas. So we count the electrons. The first thing I usually do is oxidation states. So what are the oxidation states? Oxygen, -2, carbon, oxygen, -2. Then I look at the formal charge. What's the formal charge? Carbon 0. Oxygen is 0. And we're running out of time, so let me just tell you. What time do we end at? 12:35? Oh, 12:40? We got time. This is 0. It's how we split the electrons, right? In oxidation state, we assume 100% ionic. So who gets all the electrons? Oxygen. In formal charge, we assume 100% covalent, so we split the electrons down the middle. So oxygen ends up with 1, 2, 3, 4, 5, 6. It's supposed to have 6. 0. Carbon ends up with 1, 2, 3, 4. It's supposed to have 4. This oxygen ends up with 6. Right? Well, is it 100% ionic or is it 100% covalent? It's neither. It's somewhere in between. Well, somewhere between means it's between 0 and -2. Well, I don't know that unless I do a quantum mechanical calculation. Do I have quantum mechanical? software available at my feet? No. And so I don't know it, so I'm gonna guess. Well, this is not really a guess. I'm just gonna say it's delta minus, where delta is some number between 0 and -2, right? This is polarity. The carbon's somewhere between 0 and +4, so we call that delta plus. It's somewhere between 0 and +4. And this is delta minus. And so delta is somewhere, you know, where it should be more reality, but I don't know the number unless I do a calculation, right? And then when we count octets, you know, oxygen, carbon, and oxygen have an octet, so all have an octet. These are all octets. And so where is the negative charge density on the oxygen? Is there a lone pair? Yes. And so we call this a base. This is a basic atom, or base site. The two oxygens are bases. Where's the positive charge density? On carbon. This is our acid site. But can carbon have more than an octet? Carbon cannot have more than an octet. And so how can this acid accept another lone pair? Because if another lone pair comes in here, then we'd have 2, 4, 6, 8, 10 electrons exceeding an octet. Carbon cannot exceed an octet. Okay, yes, the electrons rearrange. How this happens is this. If a lone pair comes in here, then it's going to kick out some of these. Well, if it kicks these out, it can't kick them out in space, but it can kick them out onto oxygen itself. So if there's a way to rearrange the electrons, then this can happen. And so let's take a base and show you just by example here. Water. We can do the same thing with water. And the hydrogens would be acid sites, and the oxygen would be a base site. And so we have two possible outcomes with water. If water attacks the carbon, that would be this outcome. If water attacks the oxygen, that would be this outcome here. Right? All right, when we say attack, that's a very common word. In Lewis acid base chemistry, we always say the base attacks the acid. And so if the base attacks the acid, then I'd say water attacks the carbon here. Or oxygen and CO2 attacks the hydrogen here. Which one is it? We don't know which one it is. And so what you do is you do both of them and figure out which one leads to a more thermodynamically stable product, right? We're always looking, we're going from less stable to more stable. And so it's just a coin flip until you get more experience, and then you can automatically do this usually. And so let's have the base attack. And so what happens is this lone pair here on that oxygen goes here. But now we would have 2, 4, 6, 8, 10 electrons. And so that means these pi electrons are going to be booted out of here, out onto the oxygen. And this is going to convert this from sp to, it's going to change all the hybridizations in valence bond theory. And so what we end up with is this structure like this. The structure is going to look funny. It's very funny like this. But you look at this, did I violate the octet rule? No. Everything has an octet. If everything has an octet, is this a good structure? No, this is not a good structure. What's wrong with this structure? The formal charges. The formal charge on this oxygen is plus, the formal charge on this oxygen is minus, and the other formal charges are all 0. Is this good? This oxygen has extra, this oxygen is missing. If you had a tug of war between two oxygens, then, you know, it should be a tie. And so this is not favorable. And so we'll look at this next time since we're out of time today. I went over a little bit.